Okay, so let's continue. We stay in the realm of combining optimization and learning. As Joella said, I'm supposed to talk about multi-agent deep reinforcement learning and something else. And that's precisely what I will do. I tend to talk too much, so feel free to stop me on the way if you have some questions, which will at the same time give me an excuse for going over time, right? So if somebody's angry in the end, I can say, oh, there were so many questions, so I had no chance to finish in time. Anyways, let's start. So I want to focus basically on a control problem in the AMOD setting. And I took the simplest one to understand, which is basically the dispatching problem, right? So everybody knows how Uber works. So I will make that rather quick. Basically, we're looking at a setting where you have some service area, some customers put requests into your system. So you have a fixed size fleet of vehicles with which you can serve those requests. So if you're the operator of that fleet, what you have to do is you have to decide which of those requests to serve and which of those requests to not serve, and with which vehicle to serve which request, right? And you want to do that in a way that you maximize your own profit. So the prices that you collect from the customers that request the rights, minus the cost that you have for operating your fleet. You can add some rebalancing or not, depending on how complicated you want to make the problem. I will comment on that later, how to do that, but let's stay in this dispatching notion to make it as simple as possible. The customers that show up in your system have some maximum waiting time, right? So if you let a customer wait too long, it will just take a Lyft instead of an Uber, and then you will not make profit, right? So this is basically the setting. Well, why is this a difficult problem to solve? Well, if you think about that, usually you're operating a rather large fleet with rather many customers, right? So you're facing a multi-stage problem, which has some stochasticity in how the requests show up, and it's large. And to make it worse, it has some combinatorial structure, right? Because there's a routing problem on the ground and a matching problem involved. And what I want to do with you today is basically to talk about precisely this problem from two different learning paradigms. The first one will be deep reinforcement learning, right? So the question is, how can we make deep reinforcement learning work on a rather large scale setting for this dispatching problem? And the second one will be, let's call it for now, an alternative learning paradigm. For those of you who saw talks I gave over the last months, you probably know what this will be. So that will be more like an imitation learning perspective of the same problem. And then I will try to summarize that for you, giving you some ideas on what works when and why it works and when it does not work. So let's start with the deep reinforcement learning perspective, still with some optimization flavor, right? So I will go rather quickly. If you want to read on the details, there are two papers, both published in L40C this year and last year, which you can read up on if you want to get the details on the learning architecture and so on and so on. So basically, I formalize this dispatching problem as an MDP, right? It's a discrete problem, so I have a fixed time horizon with a fixed time step size. That doesn't really matter. You could also make that event-based if you want to be more dynamic in your time horizon. It's just simpler to explain it like this. And in each time of my decision intervals, I will just take a decision on which requests to accept and with which vehicles to serve the requests that I accept, right? I model that on a graph. So Daniela talked about graphs already. I will skip the graph neural networks, but I'm curious to plug his general methodology in my algorithms, right? We just didn't have the time yet to do so. Still, I will model the transportation network on a graph, right? Where the vertices could be intersections, pickups, drop-offs, zones in your service area, and the arcs represent routes or connections between those origins and destinations. Usually you associate them with a travel time, a cost, and so on and so on. Then I need to define the state space of this MDP for my dispatching problem. Well, basically this state space contains two rather large vectors. One is the vector on the requests that are in the system at a specific time step, and one is a vector that gives me information about the vehicles that I control when operating my fleet. So for the requests, they have a maximum waiting time, an origin, and a destination, whereas for the vehicles, I know their position and the information, how long it takes them to reach one of those origin and destination stops where I want to pick up another customer, right? Such that I'm in the situation where I can assign a customer to a vehicle which is still operating another customer, right? So I will cover this part as well. Then if you look the action space, it looks rather clumsy, and honestly, it is clumsy, right? So you have like an action for each request that you get, and you can either decide to reject that request or assign it to one of your vehicles. And you further have a binary indicator that needs to make sure that each request is assigned only once. It looks clumsy. It's not really interesting. What is interesting here is that if you look at the size of that action space, you end up with something like this, right? So the size of that discrete action space is the number of vehicles plus one, because you can always reject, and it grows exponentially with the number of requests in the system, right? So that easily gets pretty huge if you have a couple of requests in your system. And usually with such a size of an action space for discrete settings, we end up in a setting where normal reinforcement learning algorithms do no longer work, right? So stable learning for discrete action spaces, it's maybe 10, 20, 30, maybe 10 to the power of 2 actions, but afterwards it can already get very tricky in ensuring a smooth convergence in your learning scheme. So what do I want to have as a reward? Well, the reward, I mentioned it earlier, I want to maximize my profit, right? So the reward that I have is the profit, which is the revenue I get minus the cost that I incur by dispatching vehicles and operating them. And in the end, I want to find a policy that in expectation maximizes this profit. Right, so this is rather standard. It's not very exciting. What is exciting is how do we do that? How do we make that work for this rather large action space? Right, and usually if you face those problems in reinforcement learning or in any optimization problem, there are two ways to think about it, right? One way is always, okay, let's decompose. And the other way is always, okay, let's somehow solve a simplified problem, right? And that's basically also what I could do in reinforcement learning. So you will find approaches that say, okay, the discrete space is too large, it's too heavy, so let's learn in a continuous space and learn some embedding that maps from a continuous space to discrete space and so on, right? This is a bit like just shifting the complexity, because this embedding needs to be learned, and usually this embedding relies on full enumeration, right? So if you go to really large spaces, there is a boundary where this will also not scale again, which is why the route I want to take is a decomposition approach, right? And this decomposition bases on involving optimization into that kind of problem, precisely in the multi-agent setting of it, right? So if you think about it, what do we want to do? We want to cook up a policy that anticipates future requests, right? So that leverages knowledge of historical data, and it needs to be scalable. So to be good in anticipating future requests and leveraging what we know about our environment, we have the reinforcement learning component that allows us to learn by experience, learn about the dynamics of the problem, and so on and so on. And I want to combine it with an optimization component that allows me to somehow capture more structure in the problem, right? And to become scalable, I will transition to a multi-agent setting, which looks precisely like this, right? So instead of learning that huge action space vector where I have all vehicle and request combinations, I will treat every vehicle as a single agent in my learning problem, such that for each vehicle, I learn an agent that tells me how likely one of those vehicles would serve a request or not, right? So basically, I train a single agent problem, assuming that my fleet has only one vehicle from a vehicle perspective, and I try to learn a score, how profitable it is to accept a certain request or not from a vehicle perspective. The problem that you get when you go into this setting is that then you have many, many agents that tend to learn some selfish behavior, right? So assume there are 10 vehicles in the city center. There's a super profitable request in the city center. All of them will like to capture exactly this request. So it's nice that I have this multi-agent notion because I can scale it, right? If I have one agent per vehicle, I can easily parallelize. So if I'm Uber, Google, or whoever, I have sufficient compute power, I can ramp that up to whatever I like. But I get something that we call in multi-agent learning a credit assignment problem, right? Because basically I somehow have to control many, many agents that all learn some egoistic behavior but it's easy to cook up some examples where you know that some of those egoistic behaviors does not necessarily contribute to maximize the profit from a system of the perspective, right? Which is why what I will do is I will let those agents learn, but I will not let those agents decide. Instead, what I will use for deciding is a weighted bipartite matching, right? So this is where I will use my optimization component. And what I will do is I will just use the, let's call it preference scores that the agents learn in a deep reinforcement learning style to inform that matching, right? So think about each agent learning a preference score on how likely this agent would like to take one of those requests. But instead of always assigning the request with the highest preference score to each vehicle, I will feed those preference scores into a bipartite matching between vehicles and requests, and then just calculate a maximum matching. And this will help me to coordinate between those vehicles and maximize profit from a global / fleet perspective and not from a per agent perspective. Yeah.
Driver and passenger there. What kind of reward scheme are we using? Are we using reward that supports the drivers or the planning?
I'm not sure if I got the question. So basically, I'm still in a deep reinforcement learning setting, right? So the question is, what kind of reward scheme do I use? So in this setting, basically, you have to define that reward signal yourself. And the reward signal we defined is maximizing your profit. Yes. Yeah, for each driver, but then you sum it up. So in the end, it's a system perspective. Yeah. So it might be, you might get a higher overall profit if a driver accepts like the second best or third best request. Yeah. Yes. Yeah. Yes. So basically, you learn an agent for each vehicle. And this agent then has an action / a preference score for each request that is in the system at time t. Exactly. Yeah. Yeah. Okay. So that's basically what I do, right? So basically, I have a credit assignment problem, and you will find a lot of literature on how to handle credit assignment problems, how to construct reward signals that coordinate the agents. I will ignore all of this, right? And instead of doing this, I will just use my bipartite matching to coordinate between the preference scores of the agents. Looking at the time, I started a bit late. Still, I think I should just speed up a little bit to not stress the patience of the next speaker and everybody too much. So I will do that rather quick. You can read it up in the paper. This is basically the scheme on how we modify the weights that we pass to the matching. So we tested different approaches there. One approach was just, okay, learn that preference score for each request and feed all of those preference scores to the matching, and you get a rather rich matching, right? Which is clumsy to solve. So what we do is basically for each of the actor networks, we learn a categorical probability distribution, right? So a probability on whether to reject or accept for each request. Think about it as a binary classifier where you have a softmax and then you will take the argmax if you want to do your decision afterwards, right? Then there are some requests that are just infeasible, right? Because a vehicle may favor a request but cannot reach it in time. And instead of relying on the DRL agent learning this infeasibility, we just mask it, right? So we have a deterministic check. If something is infeasible, we mask it and we don't feed it forward. And then during training, we sample from this reject accept distribution on what we feed forward. During testing, we will take the argmax, but basically depending on whether we have a reject or accept decision on this specific pair, we will then feed to the matching either a score of 0 or the acceptability probability, which you can interpret as this preference score. Right, so basically we have some manual mechanisms in there to sparsen the matching, so that by already feeding zeros for what we reject and having an arc max there, the matching that we have is rather sparse, right? Which makes it easier to compute it fast. So all of you know New York taxi data, right? So I will skip that to save a bit of time for the second half of the talk. We tested that on New York taxi data, on small instances, on large instances, and so on and so on. We have two benchmarks. One is a greedy benchmark, right? So where whenever a vehicle can serve a request within the waiting time and it gets a positive profit, the vehicle accepts it or otherwise rejects it. And if we have a tie, we assign it to the closest vehicle. And the second benchmark that we have basically bases on this famous paper of Javier Alonso Mora and Samita and those guys, where you just do an MPC approach, right? So I sample from some distribution, and then I solve my favorite mixed integer problem or some kind of problem to get solutions. So what do we get? Well, this is what we get. So what you see is the performance of the MPC or the reinforcement learning over, compared to greedy for different numbers of vehicles, right? And what you can see is that with the reinforcement learning approach, we consistently outperform greedy on average by 2, 3, 4%. For those of you working on similar problems, you may know that greedy, although it sounds simple, is a rather tough benchmark to beat on those kind of data sets where you have a lot of autocorrelation in the data. I was once talking to a practitioner who told me, okay, look, the best strategy we found to operate that system is whenever a request comes in, we send 2 vehicles. Try to beat that. And it was not so easy to beat that. And greedy does something similar, right? So greedy is a rather tough benchmark. And also if you look at papers from the DD group and other groups working on this, reaching 2 or 3% improvement, it's usually what they reach, right? And going much further up, it's often difficult because of the autocorrelation in the data. What was interesting to see here is that for the MPC, if you have a bottleneck on the data and you sample only one MPC scenario, then you may be even much worse than greedy, right? Whereas the RL remains rather stable. On the other hand, when you go to larger fleet sizes, MPC sometimes even was better than the RL approach, right? The more vehicles you have, the less scarce your bottleneck resource is, the easier it is to learn a good policy, right? So the obvious question that we had was, okay, why does our RL approach get worse when the problem gets easier, right? So that seems fishy. So the RL is more robust. I skipped that in the sake of time. What I would like to share with you is understanding how to make that even better, such that in those cases where the RL suddenly seemed to decrease in performance, or at least not match other approaches, you can improve on performance, right? And basically what we did is we kept the architecture as we had it. And then what we changed was the calculation of the rewards when training the agents, right? I told you I skipped all those credit assignments problems. That was only true until now, because then if you dig a bit deeper, there are different reward structures that you can infuse to solve those problems and to try to coordinate agents, right? One would be a local reward structure. This is what we had. So you just let every agent learn maximizing the local profit of the agent, and then you have egoistic behavior. What you can try to do instead is focusing on a global reward structure. So try to train the critic if you're in an actor-critic setting, which we had in this talk, based on the sum of all agents' rewards, right? So I'm in a setting where I train one neural network to encode my agent's policy, and I train another neural network to approximate my Q values with which I inform the learning of the policy network. And what we did there to improve is we leveraged a scheme which is called COMAR. It's counterfactual something. I was never good at remembering all those abbreviations, but this is basically what we do when we train, right? So the Q or the reward signal that we send back to the actor is no longer just the critic signal, but is an advantage which basically reduces the Q value by a counterfactual baseline. And this counterfactual baseline tells me in expectation the reward that the agents could have contributed to the system when taking some other action. Right, so this is basically the baseline that I subtract to get a better feeling for how important it really is that this particular agent serves this particular request. Right, and if I do this, what I see is that I can improve upon what I had before by 2, 3, 4 more %. Right, so I still use the optimization component to coordinate the agents, but I use a better quality reward signal when learning the preference scores for the agents. And then I can increase in performance again by 2, 3, 4%. And then I will also outperform the MPC in those larger vehicle settings. So that's it for the first half. Now it might get a bit tricky because I need your mind to shift from your reinforcement learning brain to your optimization brain. I will look at the very same problem, but I will model it differently. So how am I in time? 10 minutes? Perfect, 10 minutes, I'll do it. So I will model this as an optimization problem, and I will model it on something I will call the dispatching graph, right? So this is still a graph, but this is no longer a road network. This is a graph for each of the yellow dots represents an OD pair. And if I create an arc between 2 yellow dots, it means that I can serve one request after I served the first request. Right, and in this graph, I can also incorporate the locations of the vehicles at some initial point in time, such that in the end, I end up with this graph to describe my full problem. Depending on the weights that I put here, I can minimize or maximize a certain objective, right? And I can see any path in this graph from some artificial source to some artificial thing as a feasible trip for one vehicle serving a bunch of requests. All right, and then if you want to minimize cost, you just put cost. If you want to maximize profit, let's assume we solve some minimization problem in the end, you put the negative profit on the arc. So your objective can be varied just depending on what you put on the arcs. Right, so what I can do to find a solution in there then, and this is pretty nice, is I can just solve a k-disjoint shortest path problem on that graph, such that the paths do not overlap, and I get a solution to operate my fleet. And why is this so nice? This is nice because I can do that in polynomial time, right? So this k-disjoint shortest path problem, okay, it's pseudo-polynomial if you want to be very precise, right? But it just scales based on the cardinality of the arc set and the edge set of my graph. So I can use that to even solve the offline problem. And if you ask me how fast can I solve the offline problem, but I can give you an optimal solution to the offline problem for 10,000 requests, 750 vehicles in 0.2 seconds. I can also give you one for 25,000 requests and 5,000 vehicles in 20 seconds and so on and so on. And if you need to make that really fast, you can do some sparsification on your graph and you will be able to solve even this one in a second or something like that. So I can also use that in something that is computationally less challenging. So I could also solve the online problem, taking a classical model predictive control approach. I do a rolling horizon. I have a time step. I have requests in my system. I run my algorithm. If the time step is very small, that reduces to a matching as we had it before, right? But I can still solve all of this with this one optimization problem that I have. So what I want to do with that is again, do online decision making. And I still want to do learning, right? So I want to combine this optimization problem with learning. So what interests me here is precisely those two guys in the middle. So this is some deterministic mapping to get my requests into this graph shape. So I don't care, right? And this is some deterministic mapping to get the actions for the vehicles out of the paths that I compute. So the interesting part is how to combine machine learning with a combinatorial optimization layer, right? Or from a learning perspective, how can I embed a combinatorial layer as last layer in my neural network? And the idea is, if I do that in a smart way, the neural network will give me the weights of that graph, and then I just run my shortest path algorithm and I will get a good solution, right? So I can infuse even more combinatorial structure than I could do in the deep reinforcement learning setting. and I can capture anticipative dynamics with the neural network. And this is precisely what I will do. So what I will do is I will try to parameterize this neural network with imitation learning. So I have some past data. I can solve very large instances. So I will solve that instance for 1 day. And then I will just slice it and say, okay, this was the optimal solution if I would have known what happens. I will get slices. So I will get a combinatorial data set of training samples. And then I will try to learn my neural network in such a way that it gives me a theta, which is the weights of this graph on which I run my algorithm, that when I run it, the distance between the solution that I get and the optimal solution that I had gets minimal. Right? So similar idea, combined learning and optimization, very different learning paradigm. I will not learn by experience, but I will learn by imitation. So basically the idea is, okay, how to set those W's or thetas to trigger a respective solution in that setting. This sounds nice. It is a bit tricky because if you think about this loss function that minimizes between the solutions that I get and the solutions that I have as targets, this is highly degenerate, right? So this does not even have a differentiable gradient if you think about the combinatorial optimization layer. So what I will do to make that work is I will perturb the theta that the neural network gives to me with some Gaussian mass vector times some scalability factor. Right? And if I do that, then I get a loss function, which fortunately is smooth, convex, and so on and so on. And if you want to read up on this, you can look into the paper. It gives you something for free, which you can also show, which is that this Gaussian perturbation is nothing else than putting an L2 regularization on your problem. But it's much easier to implement it with this perturbation. Right? So what happens there visually? Well, if you look at this visually, think about your combinatorial problem, where the solution that you want to find is always one of the corners of the polytope of your solution space. Right? So you're always on the convex hull of that space, which is why you're non-differentiable. By adding this perturbation on your theta, you're basically changing that optimization direction such that it sometimes points on this corner, sometimes points on this corner, sometimes points on this corner, depending on how much you perturb, you can also cover the other half. Right? Such that when evaluating your loss function, in the end, you're evaluating the blue hexagon, right? So you're evaluating an expectation over some combinatorial elements. And this is what makes it smooth. And if you look at how the gradient of your loss function varies between what you have without perturbation, where it's 0 in the dual fan, and what you have when you have the perturbation, where basically you push the area where it's 0 inside of the cone, then you get the gradients that you can compute because your expectation will still revolve around the boundary, right? And then you can learn a parameterization of your neural network. So this is the second paradigm that I will use. The idea is, how good does that work? Right? So I will again compare that to the MPC approach, to which we also compared the reinforcement learning. And then I will have two of those pipelines. One, which is pure learning based on this pipeline. So I have an extended horizon where I have artificial rebalancing zones, and I try to learn how valuable it is to rebalance. And the second one is a sample-based approach where I still sample from some distribution and learn how valuable it is to capture those requests. Right? And this is what you get. What you see is, for MPC, a similar dynamic as what we had in the reinforcement learning results. For this imitation learning-based pipeline, you get something that we didn't expect because the green line is the pure learning, and the orange line is the learning with distribution information, right? Where you sample some future requests. And surprisingly, that worked better than the pure learning. And why is this the case? If you look at the solution from the structure, so here you have the offline full information bound, right? So the red dots are idling vehicles, the orange ones are transporting, and the blue ones are driving. You have no rebalancing because it's full information. Here you have the MPC, here you have the hybrid approach, right? So imitation learning plus distributional information, and that is pure learning. And what you see is that the pure learning approach rebalances way too much. So you will see way more green dots in the pure learning approach than in the other ones. So somehow you're wrongly estimating what will happen in your dynamics. And this is why you get a worse performance. And if you think about what I told you, so that looks simple, but trust me, it took 6 months to figure that out. So we had 6 months where we didn't know why that one worked better than the other. But now we know. And if you think about it, I make a fundamental mistake in this imitation learning paradigm if you look at it from a reinforcement learning perspective, right? Because the loss that I'm minimizing is this one. So I compute full information policies on past data. So all the transitions that I see during my learning stem from those optimal policies. And those anticipative policies capture only a fraction of my state space, right? And what I would like to learn from a theoretical perspective would be minimizing my loss in expectation over transitions that stem from some policy, right? So basically, I am very poor in terms of exploration when I use that second paradigm, right? And there are things on how you can solve it, right? You can say, okay, let's train on a stochastic mixture policy where I sometimes use the samples from my optimal anticipative solutions, and sometimes I add some random actions from some distribution, but that is almost epsilon greedy in deep reinforcement learning, right? So if you then take this imitation learning paradigm and do this, then you're somewhere in between DRL and imitation learning, which is why I think it's nice to point at those learning paradigms, because what you can see is that in this setting, with some distributional information, you get better performance than with the DRL and better performance than with the MPC, with the imitation learning paradigm. There are also problems where the other one will work better. You will always end up at a point where you somehow fuse optimization and machine learning from some learning paradigm perspective. And this is basically also the last slide, and I think I stressed, well, it's only 2 minutes too much, right? So I'm almost good. For me, that's on time. Yeah, but I made the summary already, right? So I think the key takeaways from this talk is, if you work in optimization or in machine learning, talk to each other, because we will see more and more approaches that use methodology from both fields to overcome problems that we had, right? So here it basically is having some optimization layer in your learning-based approach helps to either overcome scalability issues, which is what we had in the multi-agent learning setting, or to infuse even more structure into your overall pipeline as we had it in the imitation learning setting. That can scale very well, and you will handle the combinatorial aspects properly, right? Think about what I told you on the data. So sometimes there's a lot of autocorrelation, right? So even if from a theoretical perspective, it's stupid to train on something anticipative from a single policy or a single scenario, it can work pretty well in practice. So you can just test it. And if it doesn't work, then you can try to explore better and take the heavy machinery to get an even better solution. And in the end, what you will find more often in all of those approaches is that there is some OR knowledge that you can use to make those algorithms work. And with that, I'm done, and thank you for your attention. Any quick questions? Otherwise, I would say in the sake of time, or I'll be here in the coffee break and later if you want to chat. Perfect.